Next, yes, there will be. So hello everybody. Hi everyone. So we have 2 more lectures to go and plenty of time because I would like to finalize this support vector machine chapter that we started last week. Probably we'll do that today. So there will be one complete session next week that is for questions and answers. So questions from your side and answers from whoever can answer them. So this is a disclaimer. So next time, I mean, if you want to prepare some questions, that would be good probably, right? So, I mean, you have 1 week to look at everything that we discussed, look at the lecture notes, see whether you have questions and or concerns or whatever, and then we can discuss them next week. Okay, good. Then, so we stopped last time. Well, I mean, we discussed the support vector machines, and we came to this idea by looking at the binary classification problem. Okay, so binary classification problem. We said, well, if the data was linearly separable, so if you could find a hyperplane that separates your data points into one class and into the other class, then there is infinitely many of these hyperplanes that minimize the 0-1 loss. Okay, so because you can strictly separate them. And so among these hyperplanes, support vector machines aims at finding the one that allows for the largest margin. It means you have this hyperplane in the middle, and the hyperplane can be like blown up with a margin, and you stop the blowing up as soon as one point, as soon as the boundary of this margin hits one point in your data set. So that was somehow the idea, and we came to this problem here. So that was what we did last time, and we came to this problem here of formulating the corresponding optimization problem, which was this one. So we wanted to minimize this norm of W, right? That was somehow the reciprocal of the margin, and subject to, and these were the constraints on the other side. That means whenever I have this hyperplane W transpose Xi minus B, all data points should lie on the correct side. And that was this problem where we stopped. And then we zoomed out somehow and said, okay, let's look at this optimization problem in a more general context. And that led us to the general problem of convex optimization. And yeah, so and you know, machine learning and solving these problems are always or very often optimization problems. So there is no, I mean, you can rely on your local optimizer if you want to do machine learning, but you can also have a look and see what these problems are, because the better you understand your optimization problems, the better you're able to build modules and machine learning modules that solve your problem. Okay, good. So so this is why we will have a look into that. And we have this problem of minimizing a function f of z, and we have some equality constraints. Ci of z is 0, and we have some inequality constraints where we say, okay, Cj of z is greater or equal to 0. And that's where we want to have a look at. And by the way, there are many, I don't know whether I mentioned that last time, but there are many good books on convex optimization or optimization in general. It's a very well understood mathematical theory that helps machine learners a lot. Okay, so this was the picture. I don't want to go much more into the detail of that picture, just to say that we have a motivation to look at what is called the Lagrange function. And the Lagrange function consists of the unknown Z that we want to optimize, and the so-called Lagrangian multipliers lambda. And and the result that comes from Karush-Kuhn-Tucker is that whatever solves us, so I mean, if we have a pair Z star and lambda star that solves our optimization problem, then this pair satisfies the following conditions. And that's where we stopped last time. And I would like to go in there and have a closer look at what these constraints really mean indeed. So the first constraint, 817, is that the gradient of Z of this Lagrangian function is 0. So that was essentially the picture that I draw. Okay, it means that the gradient of the cost function at an optimal solution and the gradient of the the gradient of the constraint set point somehow in the same directions. Okay, then 818, 819 are the constraints. Well, I mean, that just means that this Z star satisfies these constraints. They are also called feasible solutions. So points set that satisfy the constraints are also called feasible solutions. Then, interestingly enough, in equation 820, it says that the Lagrangian multipliers for our optimal solutions are all non-negative. Okay, that is one result. And a very interesting result is actually 821. So it says that the product of, so for each of these constraints, the product of the Lagrangian multiplier and the corresponding constraint is 0. That means either one is 0, both can be 0, but at least one is 0. And if you look at that, that's really interesting, because it actually says that either this lambda I star is 0, that means that the constraints are actually irrelevant, right? I mean, they are somehow redundant and concluded in all the other constraints, so not interesting for an optimal solution. Or the constraint is 0, so that means that actually the inequality constraints are actually also equality constraints. Okay, so so this is interesting. If you take some time and look at that and also think of the picture that I've drawn, it's not so much it's not so surprising that this is the case, but nevertheless, it's really interesting that it holds true for a quite large amount of constraint functions. I don't want to go so much into the detail what the constraints are, but it's really valid for quite a general set of optimization problems. Okay. So the rest, I mean, the outline of this, how do we cope with support vector machines in that problem is, we have our optimization problem, the concrete optimization problem. We have these Karush-Kuhn-Tucker conditions on the other side, and now we want to bring these things together and see what the outcome is. And but before we do that, we look at what is called Lagrangian duality. So the motivation we look at this Lagrangian duality is that it will ultimately allow us to formulate a kernel version of the support vector machine. So that is our motivation. Okay, so let's have this optimization problem. We want to minimize the function f of z subject to our constraints. Yes, yeah. We have the equality constraints and we have the inequality constraints. We have our Lagrange function as usual, but I will. So we have our Lagrange function L z lambda is this f of z. I have here the minus sign minus sum inequalities, inequality constraint together of the sum of these Lagrange multipliers lambda I times Ci of Z. And these Lagrange multipliers are also called dual variables. Right? Yes. So if we look at this Lagrange function, if we know from the Karas-Kuntake theorem, tells us that the lambda I are non-negative, right, for all dual variables of interest. So that's good, because if we restrict to all of to all sets lambda I that are non-negative, we can see that that this part of the story, for all non-negative lambda I and for all feasible solutions Z, that this is also somehow non-negative, and that means that the Lagrangian function Z of lambda is always right. I mean, you take the cost function f of z and you subtract something non-negative, so this Lz of lambda is always smaller or equal to the f of z, right, for all feasible z and for all lambda I greater or equal to 0. And remember, feasible means that for all z that satisfy the constraints here. Okay, so there is a gap between the value of the function f of z and its Lagrange function. And if we look at, if we fix a z, we can look for which lambda is this gap the largest gap. Okay, so that means we are interested in looking at this part here. It's always also written down on the slide, but so we have this f of z minus L of z and lambda, and we want to look at when is this gap sorry. Wait. That would make it too complicated. So, right, I mean, we have this f of z, and we have here this minus, we sum up over all our constraints. F of z, and we want to see for which of the z the difference between f and its Lagrange function is largest, or otherwise spoken, for which that the Lagrange function here, which that the Lagrange function here is the smallest value, right? And this here is a function that only depends here on lambda, and it's called the Lagrange dual function. Okay, the Lagrange dual function says that it's say here the worst case in dependence of lambda, if you want. So I mean, this is the gap that you do. Is that so clear so far, Umer?
Yeah.
Okay, good. And so, and if this is the worst case, you can say, well, under which condition can we minimize the worst case, right? So when is this worst case, let's say, not too bad, okay? And this motivates us to look at a maximization of this lambda, right? I mean, so what we do now is we are searching for a lambda for which this worst case is not too bad. So we want to maximize this Lagrange dual function. And this is the so-called dual problem. And the dual problem says we want to maximize here overall lambda, this Lagrange function g of lambda subject to all lambda I are non-negative. And the and we know that for all lambda I greater or equal to 0, the g of lambda, so the value that you get here, is smaller or equal than the optimal value of the primal I should have learned to write on this thing. So optimal value of the primal problem. Okay, and if we are happy or lucky or whatever, then we can find a lambda star where this gap goes to 0, right? So where here actually we have an equality sign. So, and this is called then strong duality. Okay.
Yeah.
So strong duality means strong duality means that strong duality means that the minimum of the minimum value actually value of the primal problem coincides with the maximum value of the dual problem. Okay. And so, I mean, this helps us in particular for our SVM problem, but it also helps in general to look at that because it it allows us to compute a lower bound on the optimal value for our optimization problem. In particular, because this dual problem is always a concave problem, so it's minus a convex problem. And even if the original problems are more complicated and not easy to solve, the dual problem is always can always be solved with convex optimization tools. and under certain conditions, which I don't want to go into detail, we can compute the best value of the problem. So, yes, but not much more into this optimization unless you have some urgent. Okay, so because if you look at this
No,
level,
I think it was a bit interrupted in the middle.
okay. Okay, so how does it help us in practice? So we have here this Lagrange dual function. Okay, so the T lambda, and this T lambda is the smallest value of the Lagrange function given a certain set. So this infimum of Z can be sometimes we have sometimes, and this is also the case, it's a support vector machine, we will have a closed form solution for that G of lambda, right? And it's the equivalent. I mean, it's the same thing. Like we know that under which conditions this LZ of lambda will be small. Well, if everything is well understood, for example, if this is convex and whatsoever, then the infimum of this set is just we build the derivative with respect to Z, and then we say, okay, so Z is a minimum, and then we plug in the minimum in the function, and then we have the minimum value. So we can obtain a closed form solution of this G of lambda. Right? And once we have this closed form solution, really a function G that depends on lambda, right? We eliminate the Z by plugging in the critical point condition. And then this dual problem that we have to solve will become easier. And it's really a problem that only depends on. Okay, so let's see how that looks like in practice. And let's look at this problem for the primal and dual that we have, perhaps after a short break here.
I think, yeah, we're already 20 minutes into them.
So then let's have 5 minutes. Let's do that together. And so what is the dual problem? So our unknown parameters Z is here W and B, right? So it's a vector in RP times R, right? So these are the parameters of our affine decision function, or the equivalently the parameters that define our hyperplane. So this is, and then we have just to plug that in. So our Lagrange function is L, so W and B are our unknowns. This vector lambda is the vector of our dual variables, or Lagrange multipliers. And we have just to plug that in, right? The cost function was 1/2 norm of W squared. Okay, and then we have our constraints here that were just inequality constraints, but this is the sum of I, and then we have the lambda I. And then our CIs from the last section are here the constraints yi times, and then there was W transpose xi minus B minus 1, right? That seems to be the correct Lagrange function here. And this can be written as, if I want to bring that together, sum over I, lambda I, yi times W transpose xi minus b plus, and this here is the sum over the lambda I. Okay, just a manipulated form here. Okay, now the the question is, what can we find out about our best W star and B star and lambda star? This is the question. And the Karash-Kuntaka conditions, so the first one said that the gradient of this Lagrangian function with respect to our unknown z is equal to 0, right? And this is the first KKD condition. It says that the gradient here of and here's the gradient with respect to W and B, that this is 0. Okay. Now, what is it? Well, I mean, the gradient here of this function is gradient is in RP plus 1, so it's an RP plus 1 vector, and yeah, well, I mean, you can all compute this gradient on your own. Should be able to do that. W P lambda, and this here is, I write it here in that form. So we have here W minus sum over I lambda I yi xi. Right, so this is a vector in RP, and we have the sum over I lambda I times yi, which is the vector in this is so not to get confused here. Okay, well, and that has to be 0. So I mean, each component has to be 0. So that gives us a condition here on the on optimal W star, and so this yields the conditions. This yields, the first part here of this vector means that W star is, or here minus sum over I lambda I star yi xi is 0, and sum over I lambda I star yi is also 0 for our optimal W star, and lambda I star. This comes from the first Karash-Kuntaka condition, and we have also the last Karash-Kuntaka condition. So from the last Karash-Kuntaka conditions, it says that our optimal solutions lambda I stars times, and then we have the Ci. Remember, lambda I star times Ci star, either the Lagrange multiplier or the constraint is 0. So that was this other constraint. So we have here lambda I star times yi, and then we have the W star transpose xi minus b star minus 1 is 0. Okay, and that and the last equation is the equation why support vector machine has its name, actually, where the name comes from. Because if you look at that, you see that, so if you look at these equations, you see that the optimal W star here, first equation, so okay, so let's okay, so the last equation that we have here means that we have our I constraints, right? I different constraints, and either the lambda I is 0 or this guy here is 0, or the constraint is 0. Okay, we say that the support. What? Support. Okay, so let's write it down, otherwise I cannot explain. So either lambda I star is 0 or yi w star transpose xi minus b star minus 1 is 0. Right? And now if we look at this equation here, we see that our optimal W star, the optimal W star is a linear combination of all the xi, right, where the lambda I does not play a role, where the lambda I is 0. Right, so most of the summands here are 0, right? Namely exactly here at the point where this condition is not fulfilled, right? Okay, so either lambda I is 0 or this is 0, which is equivalent of saying that xi lies at the boundary of the margin. Okay, so I mean, if you look at the red thing here, so there are two possibilities. Let's say it like that. Two possibilities. Either the xi lies at the boundary of the margin, or the lambda I star is 0. We only have only these two possibilities. So if I look at the linear combination of this W star, it only consists of non-trivial summands of the xi that lie on the boundary of the margin. Right? So that means that the optimal W star is a linear combination of xi that lie on the boundary of the margin Full stop. And the others do not play a role. That's the interesting thing about this finding, right? All other xi are irrelevant for the optimal solution. Okay. And all the xi that are the xi that lie on the boundary of the margin, they are called support vectors. Okay, I see that there is a question from Jim.
Yes. Hi, I have a question. Shouldn't it be like W star X be the linear combination and W star only the weights? Because we're multiplying W star with the XI's, right?
Yes. Well, you know, I mean, that's true. I mean, the sign of how the xi come into this linear combination is determined by the yi. That's true. But nevertheless, right? I mean, this here is a scalar, and this here.
I'm sorry. Okay. Sorry. Yeah, my fault. I see it now. Thanks.
No,
I was looking at the second equation and I saw the multiplication between W star and the XI's, and I somehow thought that the product should be the linear combination, but I see now.
you know, I mean, this xi is a vector.
Yeah.
Xi is a vector, and this here, the lambda I star yi is a scalar. And this here, and this equation here is only a scalar equation. Okay.
Yeah.
But you're right. I mean, the lambda i's are positive, and the yi determine the sign of positive or negative sign in which this linear combination is happening.
Okay. Yeah. Thank you.
You're welcome. So this is why this support vector machine has its name. So can we use now these equations to derive a way of finding the desired optimal hyperparameters? Yes, we can. So this Lagrangian function is now. I mean, this is really some work that every one of you should be able to do in a few calm minutes at home. So we have the L, so this Lagrange function here, lambda star. The W star, B star, and lambda star is just plug that in, and right. I mean, you have from this 1/2. I omit this W star as I do in the lecture notes, because otherwise I omit the star, right? Because otherwise it's not readable. So you have 1/2 W star, W norm of W minus, and then there are these constraints lambda I times our linear constraints yi times W transpose xi minus b, right? This was the Lagrange function. And if I plug in all the conditions that I have for the optimal value, this simplifies to the lambda I, sum of lambda I minus 1/2 sum over I and j, lambda I lambda j times yi times yj times xi transpose xj. Okay, so there is one step in between that I have omitted here. So if you don't see it at one glance, you can have to compute it yourself. Right? But this is somehow, I mean, this corresponds to the, so this is the explicit form of the G lambda, right? So it's the explicit form of the G lambda, which was here the infimum of Z of L Z in lambda. Remember? That's exactly the thing. But we have optimality conditions for the W star and the B star. We know that this is a convex problem. So the optimal W star and B star, if we plug it in, it will give us the infimum. So it will give us the smallest value for that optimal W star and B star. And so we can really plug that in and eliminate it and end up with a formula that solely depends on lambda. This is what we've done here. Okay, so this here is this explicit form of this G lambda, and then we can use this dual problem and solve it, and say, okay, so what we want to do is we want to solve the right. I mean, that was it. Remember, maximizing of G lambda subject to lambda I is greater or equal to 0. That was the thing, and this is what we want to do, and this is the dual problem of our support vector machine. Okay, so that means so we want to maximize here the sum over I, lambda I, minus 1/2 sum ij lambda I times lambda j times yi times yj times xi transpose xj, and subject to lambda i's are non-negative, and we can write that into a matrix form. Sorry, we still have not incorporated this condition here, not yet. So we have to put it into our constraints such that we do not forget it. So we have this additional constraint here that subject to lambda I is greater than 0 and subject to the sum over I lambda I yi 0. Yes, and this is equivalent to maximizing. Yes, so it's just another way of writing it down. Lambda I minus, and this is 1/2, and then we have a vector lambda transpose, and then we have a matrix, let's call it M, and times lambda, right? And we can write that here into this form where this Mij is, where M is a matrix and Mij is here just the yi times yj times xi transpose times xj. Okay. Right. I mean, this form is explicitly. I mean, this form is the same as the other form. It depends on how what you like to prefer. So in this part here, you see that actually this is what's called a quadratic optimization problem. So it's a very, very particular, very easy to solve convex optimization problem where lots of solvers are designed to solve that. So you really have this linear term of the lambda I, so the sum of this lambda I, and you have the matrix here, lambda transpose times this matrix M times lambda, and M is fixed and originates from your data solely. Don't forget the constraints here, so, but they're also easy. Lambda I greater or equal to 0, and the sum over I, lambda I, yi is 0 here. So this is an easy to solve so-called quadratic optimization problem. And it scales well, and computers do a good job in solving that. And what we will have as an output of that optimization problem is our optimal Lagrangian multipliers, lambda star. Okay, so from this we obtain our optimal Lagrangian multipliers lambda I star. Right? And now if we use this equation yeah, well, I mean, if we have the lambda I star, we know that W star is this linear combination here, sum over I, lambda I star, yi xi, right? So we get the W, so we get the optimal parameters W, okay? And we get our B star. Via the equation that we had here. We had here the B star was the yi times W star transpose, sorry. W star transpose times xi minus B star minus 1, right? Is 0, so that means our B star is, so that is true for all I that define our xi that lie on the margin. Call it the support here, we had that. So the B star here is, no, is that? No, this, it has to be like this, right, Umer?
Yeah. I'm reading. There is a question in the exam.
Okay, so question for the exam.
I mean, yeah. But I think we can answer it later.
Right? So that means that the B star is something like, so you plus 1 here, you multiply that with yi, so this is yi, so B star is W star transpose xi minus yi, right? That should be for the B star, and then we are done, right? More or less. I mean, it holds true. This is, I mean, it holds true for all I in the support. So what you do in practice to make it more stable, right? I mean, every pair xi yi should give you theoretically the same B star, but of course in practice you have some numerical inconsistencies that you just get rid of via averaging. So in order to make it more stable, you define your B star, so the offset of your hyperplane, by just averaging here over, so this is 1 over the number of the support vectors that you have. So how many support vectors do you have that actually fulfill the constraints here? And then you sum up over all I in this support of W star transpose xi minus yi. Okay, and then you have your, so this yields W star and B star, right? And this yields your decision function f of x is W star transpose x plus B star, and you decide according to the sign of that function. So x is assigned to class +1 if the sign here of the W star transpose x plus B star is greater than 0, and you assign it to the class -1 if it's smaller or equal to 0. Well, you can put the equal sign wherever you like. Okay, so this is your ultimate decision function for this linear case. Okay, so there are now two extensions to that ideas. The first extension is how can we cope with if the data is not linearly separable? That will lead us, so that we get some additional constraints that will lead us to soft margin linear support vector machines. The idea is rather easy. And the next thing is how can we go to the to kernel support vector machines, and also the kernel support vector machines. You see that in formulating this optimization problem here, look at that, the first equation. We only use like inner products of our data points, right? We have the xi transpose xj, and you know the story with the kernel trick. Replacing that with a nice kernel would lead us to the kernel support vector machines, right? So there are the two extensions. I will sketch them in, let's say, after a 5 minutes break, and then see you again at let's say 10:50.
I have a question, Professor.
Yes.
I missed the registering for the exam on TUM 9, so I'm asking whether there's a repeat exam or not, so that I can attend.
So there will not be a repeat exam as per planned. But I think you should email or contact your supervisor somewhere. Maybe they can give you a special permission for the exam. You know what I mean?
Yeah, like what I do, like I should write an email to Professor Martin or Kleinsteuber.
No, not Professor Martin. So there's, for example, normally if you have the program, I don't know in which program you are in. So if we have a master's in communication engineering, then we have some persons who are called program coordinators. So you tell them, and then they write to some examination department, and then they allow you to register the exam.
Okay, but in all cases there will be a repeat exam.
No, there will not be a repeat exam.
There
This is my understanding. Martin can always create new repeat exams if because he's the boss.
there will be a repeat exam in summer semester. Right?
In summer semester.
Yeah. But I would go for what Umer said. I mean, try to get an acceptance for the exam. I mean, I have no objections against that. So if you can or ask the Studiensekretariat or whatever, right, and try to get registered afterwards. So there is no. I mean, we don't have any room plannings today this year, so it's absolutely no problem for us to integrate you into the exam, right? If you want to do that. I mean, if it's just a question of whether you miss the deadline or not.
Okay.
Yeah.
You.
So I think Tobias also messaged that he mentioned an email address, master@ei.tum.de.
Yeah, I will be emailing them now. Thank you all.
Okay.
Good luck.
You're welcome.
Okay, I just saw that I was somehow miscalculating the slides, at least the title of the slides, because this here, of course, is not yet the soft margin SVM. It's just it's still the primal and dual problem for linear SVM. Same here, and same here, right? So don't get confused, because soft margin linear SVM is something that we discuss now. So it's the soft margin linear support vector machines. And the idea of this soft margin linear support vector machine is that that actually you do not have this linear separability, right? You have your class here and you have your class there, but you have some problems in linearly separating them because you cannot. Okay, so that's what sometimes happens in practice. And and what you do is you follow actually the same idea with this margin here, but you like penalize you penalize the distance of errors that you make. So that's the idea behind. So we allow for these wrongly assigned data samples, right? But we're searching for a trade-off between having a large margin on the one side and a small degree of misclassification on the other side. Okay, and the misclassification is quantified by a set of additional variables, and that looks like that. So we have this, we have this minimizing this margin thing, and maximizing the margin or minimizing this W, right? That was fine. And then we had here subject to, we had these constraints, right? That the yi, so the classification of our W transpose xi minus b was here greater or equal than 1. Right? This is our traditional problem, our original problem. And if the data was not linearly separable, the intersection of the set of constraints would be empty, right? So we would not find a W star and a B star such that there would exist any that would satisfy any of these constraints. Okay, so what we do is we introduce here in the soft margin SVM, we introduce an additional variable. This here is minus xi. Okay, for I is 1 to n, and we say that the xi are all non-negative. Okay, and this is somehow the amount of misclassification, and we have to and we want to we don't want to pay so much for this xi. So the xi somehow costs us money, and we don't want to pay a lot for that. So the minimization problem here has an additional term. Let's say not only we want to minimize this norm here, but we also want to minimize here the sum of these xi for I is 1 to n, and we give here an additional weighting parameter c that lets us control how much we want to pay for it, right? So you get it does not work as at the blackboard, like blackboard. Okay. So if if we have to, if we probably need some compromises, otherwise we cannot fulfill the constraints and no feasible solution exists. So the compromise is this xi. The xi is greater than 0, but we want to have the smallest compromise as possible. And then we give this weighting factor c here and say that, okay, if c is large, that gives a lot of weight to our xi. And we say, okay, so we are really greedy, right? The big great C says that we are greedy, and the smaller c says that, okay, so we're not so greedy, we can allow for a larger margin. Okay, so that's the idea. And interestingly, so you end up with actually the same setting. You can now come with your Karash-Kuntaka conditions, and you can formulate that, and you can come with your Lagrange multipliers, and it's actually, I mean, it's a straightforward computation that really is not even more difficult than what we just did. So you can try to do that at home, or I mean, really try to do that at home, and or have a look at the lecture notes. Interestingly enough, is that this yields us so the same procedure. Same procedure as before. As before, leads to the dual problem. The dual problem here, lambda, is sum over I, lambda I. So it exactly looks the same. You have minus 1/2 lambda transpose times this matrix that I called M times the lambda. The Mij are again nothing else than the Yi times Yj times Xi transpose Xj. And interestingly, we have that the lambda I are non-negative here. So this is nothing new. We have that the lambda, we have that the sum over I, lambda I, Yi are 0. So this is all remains the same. And the only thing where we have an additional constraint here is that the lambda i's also have to be all smaller than the c. And this is exactly the c from above. Okay, so this is what you will find out if you really do the same procedure as we did before.
With the introduction of basically the soft margin, we have also added an upper bound on the lambdas.
Exactly.
Yeah.
Exactly. So the introduction just gives us an upper bound on the lambdas, and the upper bound is exactly the weight with which we want to penalize our our trade-offs that we have to pay. Okay, so this is the good thing here, and everything else is in complete analogous to the way before. Yeah, so that's a good extension. Actually, it's not much of a difference if we have linearly separable data or if we have not linearly separable data, but if we like penalize the size of the margin and make it as small as possible, right? That is one thing, and yes, so and then we go to this to the kernel version of the support vector machines, and actually the only thing that we Hold on. Ich würde bei beibehalten. So the classification of a new data point using kernel support vector machines is actually the only thing that we have to consider. But let's put that aside for the moment. So, you know, I mean, kernel support vector machines, we have this kernel trick, and the kernel trick tells us to replace xi transpose xj whenever it occurs by a kernel, right? Xi xj. So this is it, and we have this. This is doable if we look at the. This is doable if we look at the dual problem. So the dual problem was maximized here over lambda, sum over I, lambda I minus 1/2 lambda transpose times m times lambda, subject to. So we directly go to the soft case where we upper bound our Lagrangian multipliers, sum of the lambda I yi is 0, and m is defined as the lambda yi times yj times, and here we use this kernel function xi xj, right? So that's an easy thing. It's also easy to solve. It's still a quadratic optimization problem, and if we look at, and this is the classification of a new data point if we use the kernel support vector machines. So usually is you look at in the linear case, you have here the sign of the W transpose times x minus b that assigns a new data to your new class. Okay, and if you remember that the W that you have is the sum of the sum of the lambda I xi, sorry, yi lambda I xi for the support vectors. You have here the sign of the sum. Well, if you plug that in, you will also end up with the inner products. So this is the sum over I, and it's yi times lambda I times xi star transpose times x minus b. We'll put the b aside, but it will be the same trick than before. Right, and this can be replaced by a kernel xi and x for the new data point. So you can compute the sign here. And the b, So the only thing that is left here to compute is the B, but the B, I have no slides left. That's a little bit the problem. Well, I can use these ones here. And the B, how to get B, that's the question. Are you back, Umer?
Yeah. So there was a bit interruption.
A bit interruption. So how's the internet in Pakistan?
So the internet is good, but there was a bit interruption because the device is not charging well. I have this device.
Oh, okay, I see. Okay, good. So as I said, so the B star has it's completely the same than what we had here. We just plug that B star in this kernel version, and we see that we can formulate everything with the kernels, right? And that says that the B is here. Sorry, that the B is here the same. Then you sum up, right, of the support. So all xi training data where our constraints are really valid, where the lambda is non-negative, and where the inequality constraints are actually equality constraints. And you have here these multipliers lambda j, and you have your yj. And then you have this inner product xi and xj, which is replaced by the kernel kxi xj, right? Yes, that's actually this sum here, and you subtract here the minus y I, and this holds true for all I. Okay, so and then again, to make it more stable, you can average overall I that lie in the support. Okay, so you have the support here twice. So first of all, it holds true for all I in the support. And here you have the support by replacing the W star with being a linear combination of all support vectors. Okay, so that's the thing here. Okay, so it's completely analogous to what we've done in the non-kernel case. Good. So that would be it. That would be it from my side. So what I I'll recommend you to do is have a look at these derivations. As I said, it's not difficult, but it's good if you have done it once on your own, like building the derivative, plugging this equation to see what's going on, and also see how this inner product then occur. Right? I mean, it was perhaps a little bit fast what I did here, but it should sketch you quite well the way you derive the things, right? And in practice, so I mean, you have everything you need. You have the kernel support vector machines that also occur, or that they can also be used in a non-linearly separable case. Yeah, so that would be it from my side.